what we're looking at here is a Lewis-Star structure for chloride ion. And we saw that chloride ion here has a negative charge. So we know that we're going to draw something with a negative charge. And something with a negative charge means that it gains electrons. And so in this case, we are going to draw a full house. So the one thing you're going to realize is when you draw an ion, it's either going to be with no electron around it with a charge, or with 8 valence electron around it and with a charge. So since this is a negative, we know we're going to draw a 8 valence electron around it. So we're going to write Cl, and then we're going to put 8 valence electron around it. We're going to put a bracket. We're going to put a negative sign. This one we're gonna balance the equation, and it wanted to be in the smallest whole number. So you gotta make sure that you're doing it smallest. You can't do it big. So let's take a look. We have here, we have 2, and we have 2, and we have 1. So we need to balance it. So we have 2 hydrogen, and we'll have 1 hydrogen over here. So we're gonna put 2 up here. And now we have 2 hydrogen, and we also have 2 chlorine, because remember that any elements behind a whole number is also associated with that whole number. And so now we have 2 hydrogen, 2 chlorine, 2 hydrogen, 2 chlorine on both sides. So therefore this is now balanced. If you are uncomfortable with leaving this blank, you can put a 1 here, but that's optional. In this one, they want you to explain intermolecular forces. While iodine is a solid at STP, and the gas is chlorine is a gas. So intermolecular forces is the forces between the molecule. So iodine, when it's a solid, it is strong intermolecular forces, and when it's a gas, it's not a strong intermolecular forces, and that's why they are flying everywhere. So all you have to do is really say that in iodine has a strong intermolecular forces, and I'm just going to write IF to make it short, and that chlorine has a weak intermolecular forces. Okay? When you actually write this up, make sure you write out the word intermolecular forces. So this question say identify one chemical property of a sodium from this list. Note that you have to grab it from this list. So there are 5 characteristics that they list here. The first two are physical. These are physical characteristics. Okay, they are not chemical. So therefore you cannot use them. The only one that you can use are these. The only one you can use are these last 3, okay? And you can write down any of that, but you have to write down those last 3. You cannot derive from them. It must come from this list. Okay, so in this one, they want you to explain why would the solid form of water, which is ice, will float on the liquid form of water when both are at 0 degrees Celsius. Now this one you actually have to read in here. And if you read in here, you see that water expand, making ice less dense than liquid water. Okay? So that is why it will flow. So you will write that down, that when water, when it becomes ice, it expands, making it less dense than liquid water. So this one is actually pulled from the reading. So this question is asking you to state the type of intermolecular forces responsible for water. Okay. Now, intermolecular forces we have such things as dipole-dipole, hydrogen bonding, van der Waals forces. And so if you take a note of here, you see H2O. And H2O has a very special type of bonding called hydrogen bonding. Okay. And this hydrogen bonding is the type of forces we're talking about. And note that hydrogen can bond with oxygen, nitrogen, or fluorine in order to form this hydrogen bonding. So what you want to write here is you want to write hydrogen bonding. Okay, so in this one, you want to determine the amount of heat in joules, okay? So the answer has to be in joules, not kilojoules. It has to be in joules, required to completely vaporize a 50-gram sample of H2O liquid at its boiling point. So we remember, you want to take a look at the table T. And on table T, you're going to look at the heat formula. And with the heat formula, you see that there are three types of heat. There's the specific heat, there's the heat of fusion, and the heat of vaporization. Since this is asking for vaporization, we're going to use this last equation right here. Okay, Q is equal to mHV. So when we do that, we're going to say Q is equal to mHV. Well, we know that M is 50 grams, okay, and HV, so you know that HV, if you go to table B on the table, you see that HV has a heat of vaporization of 2260 J per G. So we're going to multiply that by 22 60. And when you multiply that, you're going to get that Q is now equal to 113,000 joules. Okay? And that is your answer. So in this one, you want to show just a numerical setup for calculating the number of moles of SnO2 in the 3-gram sample. So based on table T, we can see that mole calculation is the number of mole over the given mass divided by the gram formula mass. So if we know that the number of mole is equal to the given mass, and our given mass is 3 grams, divided by the gram formula mass, and they gave us the gram formula mass right here of 151 grams. So we're going to put that over 151 grams. And that is the setup for calculating the number of moles. So this right here is your answer. So in this one, you want to determine the number of moles of SNL when 4 moles of H2 gram is completely consumed. So the best way to determine the number of mole is to look at the coefficient. So when we look at the coefficient, that is the same thing as the number of mole in a balanced equation. So let's take a look at SNL. We have 1 SNL to every 2 H2. So the relationship is 1 to 2. Okay, now we now know that we now have 4 moles. So we're going to put 4 H2, and we don't know what Sn is, so we set it up to be x. So we're going to cross multiply, so that becomes 2x is equal to 4. X is therefore equal to 2. So therefore, the answer is 2 mole. So Sn is now 2 mole. So in this one, we want to state the color of methyl orange in a sample of solution A. So solution A has a 2.0 pH. So first of all, we're going to go to table M. And on table M, we are going to go and take a look at what methyl orange is. So methyl orange ranges from red to yellow and from 3.1 to 4.4. So since 2.0 is less than 3.1, we're going to then say that methyl orange has to be red because that is the only possible color of those that are 3.1 or less. In this one, they want to determine the hydrogen ion concentration of solution B. Okay, so let's take a look. Here's an example given here. So if we know that solution A has a pH of 2 and its hydrogen ion concentration is 1.0 times 10 to the negative 2, then the hydrogen ion concentration of solution B is going to be similar. It's going to be 1.0 times 10. Okay, and we know that the pH is 5, so we're going to put a negative 5. So whatever the pH is going to be that negative power. Okay, in this one it says state evidence found in the data table that allow the product of the pressure and volume for the fourth trial to be predicted. So of these four columns, this is the one that is talking about the product. And we look down it, we see that it is constant. So the answer therefore has to be that the pressure times the volume, or the product of the pressure times the volume for the first three trials is constant at 0.412. And therefore the fourth trial will also show the constancy. In this one, we are looking at determine the pressure of the helium gas in trial 4. Well, given the fact that we know that the pressure times volume is 0.412, all we have to do is that pressure times volume is equal to the product on column 4 here of 0.412. And we know that the pressure is unknown. We know the volume is 1.373. And from there, we should be able to calculate out what the pressure is, and that should be, the pressure should be 0.300 atm. It's a straightforward multiplication division problem. So in this problem, they want to know the average distance between the helium atom in trial 1 to the average distance between the helium atom in trial 3. We know that if we have a container, and as the container becomes bigger, that means the volume increases, gas doesn't like to be close together. Gas like to move as far apart as possible. So in volume 1, we see that the in trial 1, we see that the volume is only at 0.412. However, in trial 3, the volume becomes bigger at 0.687. So therefore, since we know that gas doesn't like to be close together, in trial 1, the average distance is less in trial 1 than it is in trial 3. So therefore, as the volume becomes bigger, then the gas move further apart. So therefore, the gas are further apart in trial 3 than it is in trial 1.